Thank you to all the organizers for the invitation. It's my particular pleasure to present to you today a work which, in a sense, is a sequel to one of my previous talks here in this meeting. So it is a sequel to the 2020 talk on tracelet algebras that I gave, in the sense that, interestingly, in 2020, I presented a Hopf algebra on a writing systems that was defined using a lot of empirical evidence from combinatorics, so in particular from the work of Gérard Duchamp, Carol Penson and collaborators on the Hopf algebra of Heisenberg-Lie type. And it was a little bit conceptually not very pleasing to have constructed this still in a very ad hoc fashion. And then something happened. So in one of the extended communities of this meeting at a combinatorics workshop, I met Joachim Kock, and he had this impulsive reaction, oh, but this must be a decomposition space. And sure enough, we discovered that this by-hand construction indeed is a relatively sophisticated example of a decomposition space. Particularly in 21, there was one technique not yet fully developed called free decomposition spaces. And it turns out that tracelet Hopf algebra comes from such a free decomposition space. And so now 3 years have passed, and I think so Joachim has worked on decomposition spaces not only in combinatorics but more generally for at least the last 10 years. And him and his collaborators, they have quite literally written hundreds of pages on this topic. And decomposition spaces are an interesting topic also apparently from a very different perspective, where they are called two-Siegel spaces. And this was a completely equivalent but entirely independent development by Kapranov and Dikharov, or Dikharov and Kapranov, almost at the same time. So I mean, this has very different applications, more in the field of Hall algebras, for example. So I won't speak much about this. I just wanted to mention that these slides are already on my homepage. So if you wish to use them to follow the references, for example, you're more than welcome. But in any event, so decomposition spaces, the entire story starts from this. That's better. Yes. So the entire story starts from an empirical observation in combinatorics that this idea of an incidence core algebra of a poset seems to appear very often in many constructions of other combinatoric species, structures than posets. But very quickly one finds, so a poset in particular is an example of so-called one-Siegel space. And very quickly one finds examples such as a Schmidt-Hopf algebra of graphs, which I will briefly show, that are not one-Siegel. And so what is quite amazing, I think, is that one then looks more closely and finds, oh, amongst the conditions one puts for one-Siegel spaces, one has to drop one class of conditions. And one obtains what's called two-Siegel spaces, going morally one level up in simplicial degree with the conditions. And voila, one finds a structure that covers basically all known incidence coalgebras. And more precisely, so decomposition spaces in the use in combinatorics are a structure that you could call a technique in objective combinatorics. So at the outset, you are not speaking about the classical incidence coalgebras with numerical coefficients, but you speak about, if you will, a groupoidified version thereof. So at the outset, you speak about groupoid slices playing the role of vectors, or of basis elements of your core algebra. And there's a beautiful construction. And this is what, I mean, this talk is in a way an introduction to now the current version, the 24 version, which was just put on the archive in October, of a paper exactly called Decomposition Space in Combinatorics by Joachim and his collaborators. And this is a 76-page paper with relatively dense material. So what I would like to do is I would like to show you sort of a take on this material, especially highlight this interesting role how coalgebras arise in this objective combinatorics viewpoint. And in the end, I'll maybe also show how then it works for tracelets, at least conceptually. But it is in a sense more of, if you will, like a service talk. I hope I can show you some very recent materials which probably has many overlaps with this community at the meeting. Right. So the plan is, so I'll of course show you, and this is very quick to do because it's not that is not the difficult part of the composition of the definition, the decomposition spaces. And then there is a second part which I think it's conceptually, because in the end of the day, if one wants a framework for working with classical combinatorial incidence coalgebras, one at some point needs to get back these numerical coefficients, and that is based upon the theory of homotopy of groupoids, and in particular the homotopy linear algebra. And I think that is unfortunately the place where it is a little bit well, maybe not quite usual for everyone in this audience, so I will try to give an explanation of how the idea at least works. And then I'll show you how exactly to get these incidence coalgebras at the objective level and how to use this homotopy linear algebra to get the numerical coefficients back, and speak briefly about free decomposition space and finally the tracelet decomposition spaces. So, as I said, the decomposition space part is relatively straightforward. We need one basic construction, which is that of well, a category called the topologist delta. It has as objects the non-empty finite standard ordinals. So I think the standard here is that you include the zero in these definitions. In particular, the bracket 0 is a non-empty ordinal because it contains the point 0. So maybe apparently this is a difference to another version of delta. But in any event, we have a collection of maps now. So basically, one can show that since these maps all have to be monotone, it's very easy to write down a system of generators for all the maps. So any map is a composition of these elementary ones shown. And I just wanted to show them, because, I mean, again, this is the very simple part of the story. So injections are generated but just by, so the elementary ones going from ordinal n to n+1, those where you forget one of the, you don't hit one of the points in the codomain. And conversely, surjections are ones where you fuse two of the points, essentially. And I mean, one can convince oneself that this is a generating system. But more interestingly, and this apparently was motivated by work of many people, in particular of Jacob Lurie, there's a completely different generating system. And actually, this is a factorization system, also an orthogonal factorization system. And the name is maybe not very descriptive, but one class of maps is called active, and these are the endpoint preserving maps. So from n+1, so from any larger m to n, you can do anything you wish in between, but you have to keep the endpoints. That is the so-called active maps. And then another class is called inert maps, and these are essentially distance preserving. So in these little diagrams, those are the ones where I mean, all the arrows essentially go parallel. Okay, so why ever this is interesting, but now it turns out if one looks back at this simplex, this delta category, that amongst all the maps that were the original generators chosen, interestingly, the so-called outer coface maps, so the blue arrows, they are all, let me say this correctly, they're inert and all the rest are active, this way around. Okay, and later in the talk, one construction on decomposition spaces, we will shortly construct decomposition spaces, but we'll precisely hinge on this particular feature that there's a class of maps which basically read out the outer shapes that gives rise then later by left-hand extension to free decomposition spaces. So it's not, at this point, not a very clear message. I'll make it, interesting. Every time this happens, I can't. Okay. Okay, but okay. Back to the story. So the next concept we need is that of simplicial groupoids, and maybe it's worth mentioning there is a version of this theory which explicitly works with infinity groupoids already at this stage for the codomain of this functors. But let's say the latest iteration of this work, especially the version adapted for combinatorics, we just use ordinary groupoids. as targets for these pre-sheaves. So we use pre-sheaves, and I mean, maybe, okay, again, trivial observation for pre-sheaf by convention, we use contravariant pre-sheaves, so we flip all of the arrows in delta, which is why now you call them co-phase, sorry, instead of co-phase, you say phase maps and degeneracy maps. And now this is probably the intuition you would have had for simplices. So at each position, xi, we have a groupoid, and then there are some identities. And I think much better than staring at these identities is giving a quick example. That is sort of the canonical example for some sort of simplicial structure called the nerve of a category. So if you have a category, you can construct yourself exactly such a pre-sheaf by assigning to the x0 component, so basically the image of the functor of the 0th ordinal, just the objects of the category. For x1, you choose the morphisms. And then immediately already you see for morphisms you have the domain and codomain. So this gives you two phase maps. And the degeneracy map just simply maps an object to the identity arrow on that object.
Yeah, but you get simplicial set null.
Yeah, and that's completely correct. This is it's a completely degenerate example, yes. It's in that sense a bit impoverished, yes. But I think to get the idea across, maybe, and I'll briefly show later also, of course, a real life groupoid. That's just the entry level example, just to get some of the namings conventions also correct. So if at the two simplices, these code the function compositions, and again, it's impoverished not only because it's simplicial set, but in particular because in a category there's exactly one composition for each sequence of arrows. In that sense, this simplex has empty data other than what are its boundary arrows. And here's a little convention from this field. So we say that the black edges are the so-called short edges of the simplex, and the blue edge is always the last edge in this naming convention, so-called long edge. So in a way, the long edge is a middle phase map. You read it up by middle phase map. And by the way, the naming convention for the phase maps is if you label the simplex 0, 1, 2, up to n, then the di phase map deletes the vertex I, and then whatever is left is the outcome of the phase map. So in this way, one can, I mean, not particularly important, but I mean, it's nice to know this naming convention, I think. And then at the degeneracy maps from x1 to x2 are exactly these, this unitality law in the category unicity of composition. I mean, that composing the identity on an object with an arrow yields the arrow back on both on domain and codomain. These are the two degeneracy maps one has. And the higher maps would then code for associativity of composition of morphisms. Again, it's just a very basic example of this idea of these simplicial maps. But now, strangely, and I mean, in general, as you pointed out, one would really work with groupoids at each level. And now the only extra definition one needs on top of simplicial groupoids is a strange-looking condition on certain kinds of diagrams in the simplicial groupoid. And the definition is very short. It says such a functor x, such a pre-sheaf, is a decomposition space. I mean, if it's a simplicial groupoid, and on top it maps push-out squares of the simplex category where the span is an active and an inert map to these pullback squares in the codomain of, I mean, the image of that would be a pullback square of this shape. And that, of course, isn't very informative. One can parse out this definition level by level. One finds, well, that certain diagrams need to be, in general, homotopy pullbacks. And only upon closer inspection does one find a sort of combinatorial interpretation of these squares. So the first hint at what this condition means is that if you look at the level, I think it's the lowest entry, so the level 2, we'll see in pictorial example in a moment. It's something about how 3 simplices must be gluable essentially from 2, so 3 simplices are tetrahedra, and you must be able to glue them from 2 adjacent 2 simplices. That's effectively what one of these squares does. And again, I hope it's, for the moment, this is just a definition. And let's look at it now for a real life decomposition space, which is the one for which models the Schmidt-Hopf algebra of graphs eventually. So it's a nice example where for x0 you just choose the empty graph. For x1 you choose graphs, and the group weight structure here is that of automorphisms of graphs, of isomorphisms of graphs. And then at level x2 you put a partition on. You have a graph, but on top, this graph here means undirected multi-graph loops. But I mean, you put on top a vertex partition, and this induces a cut on the graph. And the cut is such that if you see this line, it crosses certain edges, and that immediately tells you that from just knowing the two parts, you cannot reconstruct the original host graph because you are missing these edges that you cut away. And strangely enough, what is possible is this diagram here, which is the lowest. I mean, this is this aforementioned structure of how simplices have to be glued together to get eventually three simplices. So three simplex is, in this nomenclature, a graph which has a three-part partition of the vertex set. And now these D1 phase maps, these middle phase maps, simply forget the last partition. They glue the last factors, like so. And these top phase maps, or the outer phase maps, they basically discard. Let me say this correctly. Entire, they delete a factor of this higher simplex. So again, like these phase maps, they pick a point and then discard that, and whatever is left opposite of it is what remains.
And by the way, the top is called D2 and the bottom is D1.
Yeah, because you have to. These have to be outer, the right kind of phase map. So the D2 is.
This domains are somehow labeled 0, 1, 2. Yeah, it's not written here.
Yeah, it's at the at the level in the groupoid. So
the domains or the boundary between domains?
No, domains.
But I mean, from X3. So X3 has indices 0, 1, 2, 3. So if you draw, I mean, better to have a drawing by hand. That's why I had the other. If you then delete 2, you read out a certain. Let me call that correctly. 2 simplex. Yes. And that would be that one in that nomenclature of examples. And for example, the D1 is a middle possibility. So always D2 would read, D2 and D0 on that X2 to X1, for example, would read out one of the parts. And the middle one always forgets the subdivision. That's kind of like a composition, if you will. So it's a naming convention which, I mean, yeah. If you parse it out, it'll be precisely the correct sequence of events. Because here, this turns out this is a homotopy pullback. So one can check that indeed you can reconstruct this X3 from the data in the span here. But again, as I said, you couldn't actually, and so the interesting thing is that the Siegel condition was including, for something like a postdoc, you would have a condition that says from 2 X1 objects embedded into X0, you could reconstruct a 2 simplex, like in a nerve of a category. You could do that because a 2 simplex doesn't carry any other information than its boundary. But here you can't. So this is simply impossible because here X0 is just the empty graph, and X1s are graphs without any markings. So embedding them both in the empty graph doesn't certainly allow you to reconstruct a partition. Okay. And so this is a first example of a decomposition space, which is 2 Siegel, but not 1 Siegel. So it's a true, if you will, example of a decomposition space. And there are many others. It's just that this one, I think, is still imaginable. Okay. And now one more structure, which is very useful, it turns out, is that of so-called Kulf functors. So once you have these, always, if you construct a class of categories, you can ask what are the kind of functors that allow you to remain in this class of categories here, decomposition spaces. And it turns out the right notion of functor to do, or map of groupoids, if you will, is that of Kulf functors. So the name stands for conservative and unique lifting of factorizations. I think this is a traditional origin from simplicial groupoid theory, but I think more practically speaking, it's functors that are Cartesian with respect to active maps. So whenever you have a square sort of homotopy pullback over an active map, then it has to be mapped to such homotopy pullback. And the nice thing is, now, first of all, whenever you find such a functor, and you know that the codomain is a decomposition space, already you know the domain is a decomposition space, so sometimes it's, I mean, these can be practically constructed sometimes, these functors, and so in this way, in quotation marks, discover other decomposition spaces. And the other thing is that decomposition spaces as objects and these Kulf functors as morphisms give you a nice category of decomposition spaces. And now, I mean, I didn't know where else to put this because this is a relatively new result by Joachim Kock and David Spivak. There's one extra interesting property, namely decomposition spaces are in general, as I said, not one-Siegel spaces or not categories, but decomposition space slices. So if you fix a decomposition space and you look at all the ways, we said that if you have a morphism into a decomposition space, that gives you a relationship between decomposition spaces. And then in a slice category, you can compare these relationships. So you can discover, let's say, longer step relationships in a nutshell. And it turns out that gives you presheaves. So suddenly you can use all of Topper's theory to reason about these relationships between decomposition spaces. This has not yet been much explored to the best of my knowledge. In particular, for example, what the interpretation of a sub-object classifier is on the level of combinatorics is, I think, not explored. But I just wanted to mention that this is, I mean, these categories have an enormous amount of structure, and this is one of the really interesting properties, because it allows you to construct examples of decomposition space bijective proofs from techniques in Topper theory, like, for example, taking disjoint unions of Topper or comma categories or something like this. Okay, but this is more of an outlier in the presentation. Because, I mean, up until now, this is very compact theory, but of course what we want is we want to construct instance coalgebras. And for that, unfortunately, now comes the part which is maybe, I mean, it's by no means as intuitive as the other part, I think, but unfortunately that's where the story goes. And the original motivation was that, for example, like in this Hopf algebra of Graphs by Schmidt, I mean, one of the immediate observations is that clearly any algebra can only be supported on isomorphism classes of finite graphs, because these partitions essentially they are ordered by blocks, but not, I mean, the vertices do not have fixed identities. So I mean, one quickly finds that one needs some sort of reasoning on instance coalgebras, but for, let's say, based on isomorphism classes. And then the immediate question is, how does one formally define, formally in the sense of machine provably formally, the transition from some categorical concept to a vector space indexed by isoclasses of objects. That's sort of the kind of operation that is, of course, well known in homotopy linear algebra. And it's just that originally, apparently, it was quite, I mean, the techniques to perform such constructions were a little bit ad hoc, because each field, especially in the field of whole algebras, for example, or there were always constructions to perform such, let's say, de-objectifications, but not something universal. And decomposition space theory really showed how to do this in a beautifully compact way, I find. And the idea is, so we are already working with these decomposition spaces. We are working over groupoids already. So let us have a look at groupoid slices. The idea is that groupoid slices will essentially play the role of basis vectors in the end of our construction. And so groupoid slices are like slice categories. So objects are morphisms into some fixed groupoid B. And the morphisms are these kind of triangles. The only difference to a slice category is that you have this homotopy in there. So basically the diagram doesn't commute, but only up to homotopy, up to natural transformation of these functors. And so, I mean, here's a reference, but I mean, the hint that this is a right choice is that there exists a natural pairing between these groupoid slices and families indexed by this fixed groupoid B. It has something to do with the Groten deconstruction and homotopy sums. And in the end of the day, this will be the viewpoint. So the groupoid slices will play the role of vectors. Let's say, imagine in a Fock space type description, and the families of groupoids will play the role of the dual basis. although dual is exactly one of the points. Okay, and so one needs one more construction. So, and it's quite universal. So if you have slice categories, it's well known you can perform some elementary operations. One of them is just pulling back. So basically change of base, if you will. If I take a morphism in here horizontally drawn, that changes the root, the target object of my morphisms. Then you can fill this diagram with a homotopy pullback in that case, because I mean it's groupoids. But broadly speaking, that is like a pullback. You can think pullback, I think, for all intents and purposes for the moment. And this functor induces changes in base between grouped slice categories, and it has a right adjoint, which is a so-called lower Schrieg operation, which is just post-composition with this morphism in the base. And it turns out that it has this combination of functors has an interesting property called Behr-Chevalley. If you have such a diagram which is a homotopy pullback, then you can use pulling to go up and then push, lower Schrieg to go right, or you can do it the other way around. And it turns out that these two outcomes are homotopy equivalent. So there's a natural isomorphism between these two paths.
Is he Claude-Chevalley?
Behr-Chevalley. I don't know. Sorry, okay. I don't know. Okay, and now combining these two things, we can construct what's called linear functors, and that will be, so in homotopy linear algebra, basis vectors will be these groupoid slices, and then the analog of matrices or of linear operators will be these linear functors. And so basically, when you have any span of groupoid morphisms, then this combination shown there gives the analog of a linear operator on the vector space modeled by these groupoid slices. Just a combination of pulling and then pushing. And because of Behr-Chevalley, such linear functors, I mean, if you do the span composition of the underlying spans, then the composite span is exactly modeling the composite linear functor. So we get a very nice category which has groupoid slices as objects and these linear functors as morphisms. And this is finally the ingredient one needs to arrive at the analog of what would be the, I think the inner product, is that correct? I mean the pairing between vector space bases and the dual bases. And maybe for interest of time, I leave this formula here. It can be computed. It's a very concretely computable formula for concrete choices of groupoids and slices. Okay. I mean, everything up to here works only with homotopy pullbacks, essentially, and this one adjunction. So it's relatively economical. And now, so the interest is now that ultimately one can do a lot of constructions in homotopy linear algebra without asking any finiteness properties. But if we want to, in the end, obtain numerical coefficients, one has to put certain finiteness conditions. So if for a groupoid we speak about connected components, and call pi 0 of a groupoid the set of these connected components, then we say that a groupoid is locally finite if the size of the automorphism group of any such representative is finite. And that will play a role because ultimately we'll take groupoid cardinality to get the coefficients, and that is one of the constraints. And then overall it's finite if also simply the support, the number of objects in the groupoid, the x0 is finite. Okay, and yes. Yes, and we reserve some name for the category of finite groupoids because that will appear a lot on the following slides. It's just a groupoid written in small. Okay. And now it turns out one can define, and this is also in the work of Bars and Dolan, one can define groupoid cardinality very simply as, so it's a cardinality of the entire groupoid is the sum over these connected components, 1 over the size of the order of the automorphism group, which of course will be rational number because we assume certain finiteness conditions here. And And you see already there's a notation which already highlights that if we have a function on this in the spaces of connect components into the rationals, then this notation already suggests sort of this idea that this is basically the coefficients are the coefficients in a basis chosen for this groupoid through these slices. Okay, and right, yeah, and so indeed one can then define. So now we have something which is the coefficients in a given basis of any arbitrary vector. Oh no. Thank you. Because yeah. So now there's an analogous formula which can compute the analog of matrix coefficients, if you will, in a chosen basis. So it's a little bit like in Fock space calculus, where you start out from defining your Fock basis, you compute a pairing, you define a pairing to choose the coefficients also of the dual basis, and then you can give matrix elements in that particular choice of pairing. And it's all done very nicely again through some sort of Cohen style formula which uses just the cardinality of the fibers over, so for two symbols which are just the names of equivalence classes. The only point in this computation is to determine the cardinality of the fibers over these 2 points, but that again is coded under the hood from the linear functor through basically collapsing the span into one from the apex to the Cartesian product of the two, and then this can be computed by standard methods. So we have a very nice formula for the analog of matrix elements, and yes, and it turns out finally that there is a nice relationship between the formula for let's say the basis coefficients of arbitrary vector in a given basis chosen by groupoid slices. And this just has to do with the trick that, of course, the span where one leg is just the leg into the terminal groupoid is a special case of this linear functor formula. And then one can show that this cardinality, this local cardinality, is just the cardinality of that particular linear functor created from the basis element. So, okay. Yeah, I mean, this is at least the calculus. But now finally, one, sorry, how much time do I have? Okay, good. That, yeah.
You have some 5 minutes shift.
5 minutes shift.
So
Really?
you decided. Well, you tell me if I'm reasonably fast, so I can stop it.
You have 5 minutes to the normal.
okay.
No, because now we have all the ingredients. So now the actual coalgebra construction is beautifully simple now. I mean, if we recall, we had this simplicial groupoid called decomposition space, so some kind of simplicial groupoid with extra data, namely certain diagrams of these phase and maps and degeneracy maps are pullback, homotopy pullbacks. And now we can look at two particular mapping. So basically, if you take two simplex, one map is reading out the long edge, the composite in the nerve category example, and the other one is just the combination of the two other phase maps at level, I think I count this correctly, 2 exactly, to read out the two short edges as a Cartesian product. It turns out if you take, so again, we had before a construction from such a span of groupoid maps, we can construct ourselves what's called the linear functor by, so basically we first pull against the D1 and then we lower shriek or push against this, this map into X1 cross X1. And it turns out that is exactly the categorical version of incidence core algebra. And then there's a similar construction for the co-unit. So no extra definitions other than decomposition space and the formula for how to define a linear functor, which itself comes from a very simple adjunction.
It would be helpful to have some example, yeah, because we have many verbs and
Yeah.
It's an example. It would really much better.
Yeah. So I think I have an example. Yeah, I'll. Yeah, but roughly speaking, the idea is that if you think of the simplex category example again, then the co-product of a map F is to be sum over all the ways it could have arisen from composition, with the two composition factors on left and right. That is the idea. What this should compute. Okay. Yeah, sorry. This is exactly. Okay. Yeah, sorry. This is exactly what's written here. So that is the classical intuition for incidence coalgebra. So, for example, if the morphisms were just so if one just models a monoid, for example, as a one-object category with the morphisms, for example, if you have the integers and the morphisms are all the natural numbers, then the coproduct should compute how, for example, natural number n can be decomposed into two natural numbers that sum up to n, that kind of thing. And the only complication is that we are working with groupoids, so we have to define what we mean by the coefficients. So because it has to be compatible with the invariance under choice of representative in this groupoid basis. And I think the closest example, I hope, so in the Schmidt-Hoff algebra case we saw, one can choose isomorphism classes of finite graphs as basis. And then the calculation here will produce precisely the sum over all partitions of the underlying vertex set. And then the left and right factor are the restrictions of the graph G to these vertices, or more precisely the isoclass of that restriction. So I think that is the most clear example I have amongst these. And I hope this provides some intuition. Nevertheless, of course, then the calculation one has to perform for the decomposition space at hand. And in this paper by Joachim, there's quite a long list and also some techniques of how to efficiently do this. So reproducing many combinatorial sequences, for example.
It seems to be non-commutative.
Yes.
Because maybe it's a good example. You have oriented graphs, and you cut only by edges. You go from the left to the right, break symmetry, which is accidental for naive graphs. Yeah, literally.
Or even more extreme in the Fadi-Bruno example of instance coalgebra. You have a subdivision of a partition which blows up into a lot of independent factors in one root case, or any of these three examples, for example. Yes. But I mean, I think let's say, formal interest is that no choices went into this other than that we work in homotopy linear algebra. And sort of the work is in showing that a certain example is a decomposition space. And then from then on, you get the definition, the concrete definition, or this is a computation procedure for instance coalgebra. I mean, not for free, but I mean, if you can compute this, sorry. Yeah. Oh, okay, but yeah. And and I don't want to go into this because of lack of time, but just to say that it turns out one can show that these strange-looking axioms that one had on top of being a simplicial groupoid were designed precisely so that so the smallest index case is a sort of relationship of these x1 simplices, which those are the carriers of bases in the system, and the x2 and x3 simplices. And it turns out that these two parts of this large hierarchy of axioms make sure that this instance coalgebra is coassociative, and well, it turns out to be co-unital by construction. But this is the core of, I mean, why decomposition spaces work the way they do to produce coalgebras. Okay, and maybe, yeah. Okay, so at least one word about, I mean, now, of course, the idea is to apply this this idea of cardinality of groupoids and of linear functors of groupoids to the special case of decomposition spaces. And well, there's a lot of technicalities in checking the right finiteness conditions. also if one wanted to do the dual version, the incidence algebra product, the convolution product, then there's even more technicalities. But roughly speaking, there's a way of showing that under suitable finiteness condition, one can extract precisely the coefficients of the coproduct by taking the right kind of Group cardinality on the linear functor that defines the coproduct. So I mean, once one has decided the right finiteness condition, it is exactly the idea of Group cardinality, or rather of linear functors of Group, but there are technicalities about what precisely you can allow in terms of finiteness. So maybe won't say much about this, but and I mean, yeah. So in this nice new version of this paper, which I think was developed over the last 5 years by Joachim and his colleagues, there is quite a large variety of examples, and I'm just listing a few here. And there's even some kind of calculations you can perform based on decomposition space theory, such as, well, this objectified version of Möbius inversion, for example. Joachim also has a paper on how this pertains to renormalization, but I think maybe this is very far outside the scope of this talk. It's just to say that there's a lot of work one can unlock in this nice new formalism of decomposition spaces. And yeah, and just to say that finally, how do we, I mean, one route to get to bialgebras would be to also look at incidence coalgebras, at incidence convolution algebras. But it turns out for many of the combinatorially interesting examples, you can follow a different route, because you can show that if you have a monoidal structure on top of your decomposition space, which already carries this coalgebra, basically this is expressed through Kalf functors that are compatible with, well, through Kalf functors of the kind shown. Then you indeed get incidence bialgebra, so called a monoidal decomposition space construction. And this nicely then also numerifies, so to speak, to the known bialgebra examples. So this is, for example, in the oh, sorry, I thought I had there would have been an example of the Schmidt-Hopf algebra where the monoidal structure chosen is just disjoint union of parts, but I mean in the sense of partitions, where you just glue blocks of partitions. Turns out that is compatible with this coalgebra structure, gives precisely then the bialgebra. And if on top you have that the x0 is just trivial and you have a grading of filtration, then you use the usual trick to get a Hopf algebra back, because you can't have an antipode, of course, in the objectified level, because you don't have negatives, subtraction of coefficients. Okay, and the final piece is, fortunately, again, conceptually much simpler than this whole homotopy linear algebra. So back in the definition of what is this delta category, there was the observation that in this other factorization system, active inert, only these sort of outermost cophase maps were of this kind. I always say the wrong way around. I think inert. Yeah. Okay, but and so that defines a sub category of delta called just the inert delta inert. And now we saw before how to take this lower shriek, which is computing left Kahn extension. And it turns out one can compute from each such impoverished, if you will, decomposition space just defined on this delta inert, a full-fledged decomposition space, which is called the free decomposition space. And this is a construction that gives many examples in combinatorics, and in particular has very good properties. It has always the structure of a Möbius decomposition space, so it's very good finiteness properties and so forth. And the list of examples covers I mean, I think the slogan is they use that basically whenever you have some structure of deconcatenation, be it words, be it dict path, be it, then you have a good chance of finding the structure. And I mean, the fun example here is that of dict path. So in dict paths, you can construct this impoverished, in quotation marks, original decomposition space is just the one which from a dict path reads out, simply cuts out the topmost or the bottommost level, and then, I mean, shifts things back together, so it's a dict path. And if you take the free construction, so take this left Kahn extension along the embedding of this impoverished delta into delta, I mean, there's no extra construction. This is just the left Kahn extension. And conceptually, what it explains to you is that now you get a decomposition space, which on top has this monoidal structure, namely that you can put, so at each xk of the new space, you can put on top to the digpath levels, like for example this one. And then you have still the D0 and D2 from before, cut stuff. But then now you also have a middle phase map. So this is a way now you get a real decomposition space that just, in this case, just forgets this marking, this level marking. And that gives a very nice formalization of decomposition space for digpath. It exactly gives you, if I'm not mistaken, bialgebra, even incidence bialgebra. Just to give one placative example of this pre-construction. And I wish to conclude this because I said in the beginning that my interest in this was that I work in some very abstract setting in rewriting theory, but I had found a need for constructing Hopf algebras. And with Joachim, we had discussed at the get-go when first I discovered these tracelets, and he was at that time working on decomposition spaces. And the thing is that, so I just give you a brief idea of what should be the Hopf algebra. So in a rewriting system, for example, here attacking graphs, each step, which is one of these little boxes, manipulates the graph locally. And then one can ask about interaction structure between consecutive steps. And as already sort of suggested graphically, there will be interactions between these individual steps, but the interactions might not, they had taken an associativity kind of property that is not very simple to describe, for example, with operats, or with string diagrams, because the interaction, as shown here in this example, in a way, you seem to have a partial graph interaction between the two orange boxes, from the output of one to the input of the other, which is only permitted because you keep one of the vertices intermittently. And it turns out this is a very intricate structure. And the idea of a Hopf algebra would be to be able to do combinatorics on this rewriting system in the sense of counting classes of such, let's say, these interaction pictures, if you will, a little bit an analogy to, motivation for Feynman graphs, maybe. And now the beauty is that, the reason Joachim thought it might be decomposition space is in this triple composition scenario. Because at first sight, it looks like if you have 3 steps, how do you get 4 projections? It doesn't seem the right number, so but the interesting bit is what you want the semantics of this to be, is that each box covers a template for one rewriting step, which when applied concretely at a graph performs the manipulation. And then a box around 2 of those with some interaction should cover the template for a 2-step interaction with a certain interaction between the 2. So there's an elementary way of classifying such boxings. So you get 2 boxings, so the first with the second or the second with the third. But then it turns out that the other 2 boxings are, because it must make sense to black box a box, so just give the net effect of such a box and see how that interacts with the next one. And that gives you exactly the other 2 possibilities. So imagine this is a tetrahedron. You're reading out 4 different sub-pieces of this interaction picture. And that's exactly what's shown here. So either you perform basically the analysis of 2 consecutive steps or of a composite of 2 consecutive steps with a third. And this is the idea, but then to show that this gives an associative, first of all, even to say what means associative anymore, because I wanted it to give rise to algebras that would ultimately be used for continuous time Markov chains. And these algebras are exactly carried by equivalence classes of individual rules, so isomorphism classes in a certain sense. How do you get to what would be a convolution incidence algebra? And it turns out, this is, I still find this fascinating that Joachim was so insistent to just stick with the program and construct a decomposition space and then look later about details how to, which exact design choices would lead to the kind of algebras we need. And the decomposition space is beautifully simple. It's, you put on the 1 simplices, you just put these individual rewriting rules. On the 2 simplices, you've put a structure which is exactly not a hollow 2 simplex, but it's the data you need for composing 2 rules in the semantics of double push-out rewriting. And the 3 simplex are really the complicated ones. They code for data that seems to be, this seems to continue up and up, but it's exactly the finding, and that is making it possible to find an associative algebra at the numerical level, that we have a decomposition space axiom that codes for these three syntaxes. Namely, you can reconstruct them up to universal, well, up to homotopy by the data of two adjacent two syntaxes, where one codes the composition of two, and then the next sticking on the long edge of that in coding for the composition of the composite with the third. And I mean, it is still interesting. So what we get from this construction is naturally the existence of these tracelets, because it's a minimal data you need. That's another way of reconstructing the C-simplex. It's like a sort of a minimal rewriting sequence, and it sits precisely in this decomposition space theory. Tracelets themselves do not yet have a formalization in the theory, but I mean, suspicion is it must be another way of analyzing these decomposition spaces. And from this construction alone, I mean, we need the incidence algebra version for this to work. But I mean, more to that detail, we get already one algebra out of it, which I call rule algebra. It's exactly the algebra underlying constructions of Markov chains for rewriting systems. And then by using an elaborate version of free decomposition space, one can get an actual Hopf algebra of these interactions. But at the time when we did this was, and the paper wasn't even fully published on free decomposition spaces. And I still find it, I mean, it's an interesting coincidence that one can use such a new theory for a problem in computer science. So it's very satisfying, I think. And then finally, just again to summarize, so decomposition spaces are a relatively new development, but already show quite some promise as a classifying construction for, at the very least, incidence co-algebras. Very often you can construct incidence bi-algebras by combining decomposition space with some monoidal structure, and there you choose some of your favorite classical monoidal structures to get the coefficients you would like. And then there's much deeper structures one can develop in this theory, for example, Möbius inversion, which I haven't spoken about. And so still in this theory, there's some interesting hints at what one could gain for combinatorics, because the way these decomposition spaces are currently constructed is still where a lot of by-hand work. I mean, often with some experience, you can use some standard constructions such as décalage, for example, on decomposition spaces to find constructions. And there is a hint that one can construct complex decomposition space from simpler ones using these topos techniques, or some standard classes of examples that can be combined in these where these cool functors. But it's still a very open field, and of course the big question is, can one find so decomposition spaces give naturally bijective proofs to Kauf functors, but I mean, can we reconstruct some of the more complicated bijective proofs? And okay, and sorry, and the last point is, there was a very nice workshop at Banff earlier this year, which was the first big meeting of the Dickerhoff school and of the, let's say, Kock, Cameo, Glaves school. And many of these videos are also online. If you wish to have a look at some of the uses of decomposition spaces, I would highly recommend having a look. And yeah, and the slides are on my webpage if you want to click the links. Yeah, thanks a lot.
Question? Okay.
Yes, I am. Thank you so much for this this talk. The Banff and the matter of your talk reminds me of the Canadian school,
yes.
Because Giancarlo Rota was very creative, initiated the in classical combinatorics with Yoni, yes. And they initiated the incident coalgebras. Yes. After this, I think it is William Schmidt. William Schmidt was a student of Giancarlo Rota, studied indirectly the graph decomposition by means of the partially commutative monoid, and after he went to categories, and Rota initiated the Möbius categories that were taken in charge with the Lassim, and so sorry for this bit of history, but I am so glad that you take the you go beyond the what they did.
So actually, in this current version of this Combinatorics for Decomposition space paper by Joachim, there's exactly a discussion of this trend starting from Rota and the instance algebra of posets over this version by Joyal, where you model it with surjections, but then you have to take a certain quotient. And apparently, the philosophy is that with decomposition spaces, you get coalgebras without having to by hand find the quotients that are necessary if you have to go through the poset route. And I mean, there was some very nice discussion how this pertains to especially this Möbius construction. The rough morale seems to be that these coefficients you get by cardinality are sometimes very hard to find by hand if you have to, you know, if you have to pick a basis, for example, by hand. Then this apparently is a technical problem in computing. But yeah. So basically, Joachim shows how the objective version of these constructions works. Yeah.
Okay, so maybe other question in the coffee break, because now we have talk by Frank Jensen.